Okay, so we're going to have a go at proving this inequality, that sine of cos of x is always less than or equal to cos of sine of x. And basically to start off, you can notice here that sine and cos are both 2 pi periodic functions. And so if you have sine of cos and cos of sine, these are both periodic as well. So basically what this means is we need only consider x between minus pi and pi. Because basically, if I draw this out, we don't know yet what the rest of the functions look like, but we do know that they repeat. So if you have one of them is bigger than the other in this region between minus pi and pi, then all that will happen between pi and 3 pi, or going back from minus pi to minus 3 pi, you get the same sort of repeating pattern, where one is still larger than the other. So we only need to consider x between minus pi and pi. And what we're actually going to do next is we're going to reduce this down further to you only need to consider x between 0 and pi over 2. So we'll start off just by looking at what happens when x is negative. So sine of cos of negative x. Well, you know that cos of minus x, this is always the same as cos of x. So this is equal to sine of cos of x for all x. And similarly, you can show that cos of sine of minus x, because sine minus x, this is equal to minus sine of x. And then you've got cos of minus sine of x, which is just the same as cos of sine of x. So what we've shown here is that these functions are what you call even functions, or they have a line of symmetry in the y-axis on this picture. So let me just explain why we can now say that we only need to consider x between 0 and pi. That's basically because if we can show that the inequality holds between 0 and pi, then you'll get a mirror image of this picture between minus pi and 0, whatever the picture may look like. So now we're also going to be able to reduce this down to what happens between 0 and pi over 2. And to do that, let's just consider, so for x between pi over 2 and pi, first of all, if you consider that cos of x, if I draw out here just a little sketch of what sine and cos look like, you've got cos, go between minus 2 pi and positive 2 pi. So for x between pi over 2 and pi, we're in this region here, cos of x is always less than or equal to 0. So sine of cos of x is always less than or equal to 0. It's between 0 and minus 1. Sine of cos of x, we're looking at what happens to sine when you're between 0 and minus 1. Basically on your picture, you're looking at a little region here where this is also negative. So sine of cos of x is also less than or equal to 0. But if we look at what's going to happen to cos of sine of x, it's going to turn out this is always going to be positive in this region, because sine of x, this is between 0 and 1 in this region. So sine of x between pi over 2 and pi, we're looking at this region here. Well, this is between 0 and 1. And then if you look at cos of sine of x, this is actually going to be what happens to cos between 0 and 1. We're in this little region here. So the largest value it takes is cos of 0, which is 1. And the smallest value it takes is cos of 1. So approximately, using decimals, this is about 0.54. This goes all the way up to 1. So therefore you can say sine of cos of x is less than or equal to 0, which is less than or equal to cos of sine of x. And this is for all x between pi over 2 and pi. So here we've actually reduced this even more so. So instead of having to consider x between 0 and pi, we now only need to consider x between 0 and pi over 2, because we've already proven this. between pi over 2 and pi. Now, to prove the inequality, I'm actually going to split this up into two different inequalities, which is slightly easier to prove. So I'm going to prove that sine of cos of x is always less than or equal to cos of x in this region, and then we're going to show that this is less than or equal to cos of sine of x. And then this implies our inequality that we're hoping for, that sine of cos of x is less than or equal to cos of sine of x. And just before we get started, I'm going to introduce a lemma which is going to be really helpful for proving actually both of these inequalities here. And this is a well-known inequality that sine of u is always less than or equal to u for all u greater than or equal to 0. And let's include a quick proof of this. Basically, you can show that u minus sine of u, if you differentiate this with respect to u, then you'll get 1 minus cos of u, and this is always greater than or equal to 0. This is an increasing function then, so u minus sine of u is always an increasing function. And then if you look at what happens when u equals 0, well, when u equals 0, you've got 0 minus sine of 0, which just gives you 0 again. So it starts off, when u is 0, you've got 0, and then it's a non-decreasing function, so it'll always increase from there. So you can conclude then, therefore, u minus sine of u, this is always greater than or equal to 0 for all u greater than or equal to 0, and therefore sine of u is hence less than or equal to u for all u greater than or equal to 0, which is what we were trying to prove. So let's apply this lemma to the first inequality we're trying to prove here. So first of all, we want to show that sine of cos of x is less than or equal to cos of x. If I just replace cos of x by u, I know that for all x between 0 and pi over 2, this region we're concerned with, we know that cos of x is greater than or equal to 0. So therefore, applying this lemma, you know that sine of cos of x has to be less than or equal to cos of x. So we're doing sine of u is less than or equal to u there. And then we've proven the first half of this inequality. So now we need to prove that cos of x is less than or equal to cos of sine of x. And we're going to use this lemma again here. So for x between 0 and pi over 2, we know that, I'll write it this way around, x is greater than or equal to sine of x. And now, if we have a think about what happens when we put x and we put sine of x inside the cos function. So you have x and sine of x as your inputs in cos. So if one of them is larger than the other, so x is bigger than sine of x, so you put a larger value in, because cos is decreasing in this region, so you put in a larger value, you get a smaller output. Or if you put in a smaller input, you actually get a larger output. So this actually implies that cos of x is less than or equal to cos of sine of x, because cos is decreasing. So you put in your small input, you put in your large input, and you get a small output, and here you're putting in the small input, you're getting the large output there. So we've concluded that cos of x is actually less than or equal to cos of sine of x in this region. So we can conclude overall then, therefore, sine of cos of x, this is less than or equal to cos of x, which is less than or equal to cos of sine x. We've now proven this for all x between 0 and pi over 2. But we've seen earlier that this was actually sufficient to show this is true for all real values of x. So therefore, sine of cos of x is actually less than or equal to cos of sine of x for all real values of x.